Welcome to our May 2024 GoldSim webinar. Today we've got Simon Ogude-Chambert from SimplXit here today. He's going to show us the ropes on integrating GoldSim and Muk3D for tailings management modeling. But before we dive in, just a heads up, we're hosting the GoldSim user conference this fall, and it's from September 9 to 11th here in Seattle. It's a really great chance to meet other GoldSim users, pick the brains of experts. You can get a glimpse into GoldSim's future roadmap and join in some lively discussions. And if you're new or feel like you need a software refresher, we've got a training course lined up as well. So, and we've got some fun stuff planned. We've got a dinner cruise in Elliott Bay on September 9th and a Mariners baseball game at T-Mobile Park on the 10th. So, all right, well, enough from me. I'm going to turn the time over now to Simon, and I'll just need to change you to the presenter. Simon, you're ready to go.
Okay. Can you hear me?
Yes, Simon, we can hear you. Yep.
All right. Well, thanks, Jason, for the introduction, and thank you for inviting me here to do this webinar. Hi, everyone. I'm really excited to share some of the research and work that I've been doing on this subject. And I'm looking forward to the discussion that we'll have, any questions and comments at the end of it. The outline looks like this. We'll start with an introduction on what exactly are we doing. I'll assume that some of you might not know necessarily GoldSim or Muk3D, so it will be kind of like an overview of like what's the integration of a Monte Carlo simulation with the 3D modeling software. Then we'll do a tutorial where we'll create a project where we'll actually connect those two models together, and then we'll get into the why and how it can increase your resilience to change, and finally kind of like a way tour of the trajectories for such applications. So if we look at the modeling of TSF geometries at the rheological scale, we're trying to store a solid with water, which is a highly complex medium that shows like non-Newtonian behavior. And it's over like very large area. It's got a lot of heterogeneity in the material, so it's extremely complex to actually model. And if you just purely look at the rheological scale, it's not possible. So we kind of like need to like lose some of that scale. And so instead of looking at the rheological level, we look at the beach scale. So basically, once you have an actual tailings, you can have your slope above water and slope below water that actually contain all the information about the hydraulics and the rheology of your material. And the idea is that we will try to deposit some volume of tailings on top of it, and also it will have some water within the system. And so we'll estimate the volume based on the tonnage and the density. But ultimately, what we're trying to do is to try to goal seek what is both the discharge elevation and the pond elevation that will actually have this specific slope, and then ultimately we'll be able to do this deposition. On the right side, you saw like a sort of like a 2D goal seeking. In reality, we have like a 3D goal seeking. So according to where you have your deposition, it will ultimately lead to different type of new topographies that you have. Once you've done the deposition, the idea is that you also manage the containment of your tailings, so you actually build the containment with it. So ultimately, that's what Muk3D will be doing. It will be about building the containment and running the various depositions. Now, that's the modeling of a TSF geometry. We will be talking about stochastic modeling of a TSF geometry. So for this, I'll illustrate it with an example from like a dry stack. So dry stack is one type of construction that's got very high solid contents. In this specific example, actually the actual site had a design with a moisture content of 9%, but in reality, it had a moisture content of 15%, which means that the slope kept on varying and it was behaving more like lava than actual dry stack. So we could do that modeling. We could use the throughput and the density to actually estimate what sort of volume we would have, and then we would use a slope, and given that the slope varies in the history, we could have that slope varying. And ultimately, we'd build a model like that, and we'll keep on doing the discharge elevation seeking for this model, topography after topography. Now, while like that looks pretty, this is just like one realization of the future. And ultimately, what we're interested in is actually, well, what does likeliness of that geometry is like, what it's going to look like in the future. So this is where Monte Carlo simulations come into play. And basically what we do in Monte Carlo simulations, we replace deterministic fixed variables, and we replace them with distributions. And just like in a very most basic term, it's a little bit like if you were trying to estimate what's the most likely score when you roll two dices, because it's fairly simple with two dices, you could work out the statistics, but you could also just like keep on rolling your dice over and over and over again, and ultimately you would get like some kind of a distribution that would show you that actually 7 is the most likely sum that you get from rolling two dices. So this is exactly what we'll be doing. We'll assign some distributions, and what GoldSim will be doing, it will sample the distributions, and sometimes you might have like a tail end. You might sample it in the tail end of a distribution, but it's also about counting what is the likeliness of those two tail ends happening at the same time. So it's not just like this. And eventually, if you run it enough times, you get a stochastic geometry. So this is the profile of our dry stack facility as it's growing. And here we've got an envelope of those results. So that's what we're seeing here. So the most likely is that it will be within this band for the front, but it could be as early as that and as low as that. So comes new questions about, well, what does that imply in terms of permitting? What does it imply in terms of containing your tailings, etc. So this is what we'll be doing. Now the question is, well, we want to go towards like a risk approach to TSF design and operations, and it's accepting the fact that there are many scales of varying things that are happening. So you've got the hydrological scale where things can happen within minutes or hours for a storm, but you've got also like the scale for your project, for the permitting, the scale for the consolidation. So there's various scales and events that are actually like working with each other. So it's like, how does that entire system like work with each other? And ultimately, we want to be able to sort of like quantify what are those likely or less likely futures, so that it can guide us in terms of, well, what is the preferable outcome and how do we get to get to that outcome. So in this example, I'll show a model that can reconciliate those scales. So on the left side, we'll have the monthly geometric modeling that will happen within Muk3D. And then on the right side, we'll have a daily stochastic mass and water balance. For the geometric modeling, we'll have a simple deposition line along like the arch of the dam, and we will be erasing the dam with the center line construction. Within GoldSim, we will have a model that does both the mass balance of how much ore is being processed with some distributions on it, and then you will have some that will go to your waste and concentrate, the rest will go to tailings with some water. And then we'll do a daily water balance as well, where we'll assess the runoff as the system is evolving. So ultimately, we've got some stochastic values for the throughput, for the consolidated densities, for the rainfall, evaporation, seepage, etc. For Muk3D, every month we will get the data from GoldSim and we'll assess, well, is there enough freeboard? If there's not enough freeboard, then we'll actually raise the dam. And if there's enough freeboard, we'll just run the deposition, and then we'll calculate the state storage curves so that actually that information can be fed back into the water balance, so that it can recalculate the catchments and the areas for the rainfall and evaporation. So that's how it's going to happen. The water balance runs its daily mass and water balance, and then we get at the end the monthly volume that's deposited, the pond operating volume, the slopes, the water freeboard that's being fed into Muk3D, and then Muk3D does its deposition runs, ultimately calculates the lookup tables, the areas, the discharge elevation, which is fed back into GoldSim. So I'll go ahead and show you this example. We'll just run it very quickly just to see how does a model like that is run. So on the right side, we will have the GoldSim player that will run the simulation, and then we have Muk3D on the left side. And we just like start the process straight away from GoldSim, and it will start raising the dam, do the deposition. It will gold seek for some time. And once it finds the deposition, it will do the run, finish the run, and then start on the new topography again. So once again, now it's done the first month, and it goes on to the second month. I will just let it run. For now, we're only seeing the volumes that are changing here. We're not seeing the full values. I'm going to show you here this model that's been run, and in this case, we have in here the tonnage that's being deposited. Over there, we've got all the different crest line and the various discharge elevation and pond elevation. Here we've got how much is being pumped outside of the pool and what's the volume in the dam over there. In this video, we're only showing 13 of those realizations, and as you can see, it's actually a total of 780 deposition runs. So I'll just let it run, and you can see that it simulates multiple times the futures of the 2023-2028, and it run every single month within that year. Okay, so this is basically what the software, the coupling of those two software will be doing. It's capable of assessing what are those alternative futures, so that we're testing multiple futures of what could be possible in terms of the tailings facility. Ultimately, it's supposed to be a guide so that we can assess what is our preferable outcome. So how does that work? We are basically using a Muk3D simulation add-on. What the simulation add-on does is that automatically it creates a server and a DLL, which actually will be doing the connections between GoldSim and Muk3D. And the various steps that you'll be doing directly within the simulation add-on. The first one is you create what is the variables that you want. So basically some variables need to be sent to GoldSim and some variables need to be sent back to Muk3D. And those variables can be floating values, it can be arrays, or it can be even lookup tables that are coming back from GoldSim, from Muk3D to GoldSim. Then the second is it will create a DLL, which is what's needed for GoldSim to actually interact with Muk3D. And then we need to build the models. So in terms of models, there's two models. The first one is GoldSim, and then the second one will be a script inside of Muk3D, and the script basically has got all the various commands that needs to be run within Muk3D according to the variables that you get from GoldSim. And then finally, there's a server which just allows the communication within these two. Okay, and then finally, you just run it from GoldSim, and then it runs the model. So for this tutorial, we'll run a quarterly deposition plan. We'll use this topography here, this grid. The model in GoldSim will be very simple. It will have the volume that you deposit as a distribution, and what is the pond volume that is within this within the dam, and that will vary with time as well. And then within Muk3D, we'll just run the deposition, and then it will give us, it will gold stick and then find us what is the discharge elevation, what is the pond elevation. So the steps will go like this. We'll define the variables. So all those variables that we have here in salmon color. Then we'll create the project, which will create the DLL, which allows us to communicate between GoldSim and Muk3D. Then we'll set up our GoldSim model. We'll set up the script in Python that allows us to kind of like line up all the various commands that need to run in Muk3D. We'll start the server and run that model. Once we're done with that, we'll just complexify it slightly. by just adding another component, because we don't want to just like discharge and keep raising the dam. At some point, we'll need to actually raise the dam wall. So we'll calculate what is the freeboard, and then we'll start raising the dam. So we'll just add some commands, update the variables that we've created, and then run the model. Okay, so let's go ahead and we'll just define the GoldSim interface. So the first step is just to define all the variables that we want to add, and in our case, it's 3 variables that we want to bring. The first one is the elapsed day, so just be used to actually initialize our simulation. Then we'll have the throughput volume and then the pond volume. Then we need to create some variables for what is being sent back into GoldSim, and that will be the discharge elevation, that will be GoldSim, and then the pond elevation. Okay, so that's it. We've set up now all our interface variables. Now the next step is we create the project that will create the DLL. We'll just give it the same name, stochastic, and that's it automatically. Those variables, the DLL has been created. It's given us a couple of files that run with the server. Okay, so now we can build the model. We'll just first start by setting up, well, what are we actually running? And we just want to start with like a small model. So we'll go with, and we'll set it up with a monthly period, monthly time step. And we'll just run it for like 50 days so that we can start with simple things. Not really a Monte Carlo simulation yet. So we just need to add the different components for it. There's 3 variables. The first one is elapsed day. So it's just to keep track of are we at the beginning of the simulation or not. Then the second one will be the throughput volume. And instead of having a tonnage directly, we'll give it what is the volume per month that's being deposited. And we'll give it a triangular distribution, so 200,000 and 300,000 cubic per month that are being deposited on that facility. Finally, we'll put the pond volume, and even instead of having like the distribution as an uncertain parameter, we'll set it up as a variable parameter, meaning that we'll resample this pond volume every single month, so that actually we make it vary. And we'll give it some volume that is a bit similar to what we have on the survey. So it's 1.8 billion cubic meters to 2 billion meters of water inside. We just need to make sure to resample it. So we resample it every month. Every month it will take a different value. And then we'll also give it a bit of autocorrelation, that the volume doesn't just go up and down randomly, which is a bit more likely to happen. So now we just want to add the component that will connect the DLL. So it's an external element. I just want to show you when we created the model, it created a PDF, and the PDF has got all the information that we need to fit it inside of that external element. So it's what is the name of the DLL. So we have the name of the DLL, then what function is to be called inside of that DLL. Function 0, and then finally we just connect those various variables. So we've got our inputs, which are actually the ED, the throughput volume, and the pond volume, and then we need to connect our discharge elevation, which will be coming straight out of Muk3D. Okay. And then finally, we just want to put the result element so that once we run it as a Monte Carlo simulation, we can actually see those results. So we'll just connect it to the results. And that will be it for setting up our initial GoldSim model. So a very basic model for now. Now we can go ahead and actually set up the Python script. And the way it works for Muk3D is that basically it creates a class that's got different functions, and those functions, in this one, is the execute function that we need to call, which has all the input variables and all the output variables, which we need to actually do something with. The way it works with Muk3D is we can actually record a macro, and then it will record all those different commands that we call with the various properties that we give it. So we'll use some dummy values at the beginning, and it will create a script out of it that we need to then modify. So we'll do a very simple deposition. We need to give it some information. So we'll give it what's our initial grid. Then we already have a discharge line as well. We give it the discharge line. We need to give it what is the tonnage, and it's just dummy value. Ultimately, we'll replace it with the variable that's coming from GoldSim. And we just need to give it like an initial elevation so that it starts the goal seeking at a specific elevation. Same thing with the pond. We'll give it a dummy value of 2 million cubic meters. We need to give it a value to start the goal seeking, and give it the wall crest, which is 308.5 in this case. Okay, so we run it. It will do the goal seeking. We just let it do the goal seeking. But ultimately, what we're after is actually the script that will be generated from the macro recording. So we'll just clear the graphics and then stop the recording. And now we've got this script that's been created. It's got the two commands, the clearing the graphics and running the deposition, and it's got the various properties that we use for it. So we'll just insert it, and we want to use those values. So for now, the throughput needs to be entered inside of this command. So the command has got a dictionary with all the various values of what we actually called it with. And so we just need to replace it. So in our case, the tonnage, which is the throughput volume, we actually replace it with the throughput variable, and then the fluid volume, we'll replace it with this pond volume variable. The final thing is the base grid. Once we run it for the first time, so when ED is equal to 0, we'll use that specific grid, which is our initial grid. But once we've done the deposition, we want that base grid to be actually the new deposition run. So we'll just, if ED is equal to 0, we'll have that first value. Otherwise, base grid will have the value of output grid.grid, which is actually just the name that comes once you do a deposition. So we'll just replace that value in some comments by our new variable called base grid, and that should be it for now. The only thing is we need to actually calculate what is the discharge elevation and the pond elevation. And for this, we'll need to import a function. So Muk3D's got an API that you can, that is documented for, and basically from Muk3D.use, for the function which allows us to process the deposition result, and let's call it the deposition result. So we'll use that function, and the function ultimately gives us another class, the class of results, which has various properties, and that we want to use is get property that gives us get the discharge elevation. Just to process what is the discharge elevation from the model run. And then this time for the pond, we'll use get pond property, and we just want pond elevation. And then finally, in the output list, we just need to append to that list the discharge elevations. Beginning output is just an empty list, and we want to append the discharge elevation. And then we also want to append the pond elevation. Okay, so that's it. The script is done for Muk3D. Now we start our GoldSim server, and we should be able to run the model. So we'll just run the model. We just test it. Now the model is doing the goal seeking. It's actually, once you do your first run, it will actually put it onto the grid where you've done the deposition. We just check the results. We can see that our discharge elevation keeps on growing. The pond elevation is increasing as well. Now we want to actually raise the dam so that we have sufficient containment. So we need to actually calculate what is that crest elevation. So we'll record a macro to actually raise the dam. There's already a template been set up, so we just need to give it what elevation we have for this specific dam, and it will raise it with an upstream construction. So there's this various template that exists within Muk3D that allows you to set it automatically. So we'll just run it, and we'll make sure that when we run it, we generate discharge points. So as we're raising the dam, we'll build the dam wall on top of our tailings. Therefore, we need to recalculate what is the discharge elevation. So that's it. We'll raise the dam. I will stop the macro. We've got that new command that appears to raise the dam. And so we'll just copy it and bring it at the beginning, so that we want to assess at the beginning of the run, is there sufficient freeboard? And the freeboard will define it just at the pond crest level minus the discharge elevation. So I'll first go to the setup function of that class, and I'll create initial values for each of the realization. So I'll say at every beginning of the realization, we'll give it that value. And during the run of that specific realization, we want to update those crest elevation. So we'll just say, if our crest elevation minus our discharge elevation is greater than a specific, is less than a specific value, then we actually want to raise it. Otherwise, do nothing and go ahead with the deposition. So we'll just, once the freeboard is too small, we'll just adjust that crest elevation to a value where we actually raise the crest elevation. In this example, I'll just put it plus 2 meters. And then we want to make sure that this raised dam is within this specific loop. And so the first thing that we need to do in here is we want to change that elevation. So when we raise the dam, we want to raise that new elevation that we have. So I'll just go ahead and put that. And then we also want to make sure that the grids, now that we're raising the dam, we've got a new grid. We want to use that variable base grid. And we want to make sure that once we do the deposition, we should be using that new grid that contains the new dam wall. So when we raise the dam automatically, it just sits in a folder which has the name of the template, which is upstream, and then it's called grid plus dam grid. Also, it created a new discharge line because we're building on top of the tailings. So we also want to track what is the discharge line with the first discharge line to initialize, which is the one that we put at the beginning of the simulation. But then once we raise the dam, we want to reuse that new discharge line that's been created as part of the raise dam command. So that's discharge line will be equal to setting is the name of the template, the dam template, and it's called dam discharge point. All right, and finally, we want to export our crest elevation. So we'll just add it to our list. We'll still need to set it up inside of GoldSim and inside of the interface to make sure this variable is actually being read there. But that should be it for this specific one. So we need to edit now. That new crest elevation will come inside of Muk3D. We just need to edit it so that it can now receive that new information. So we split crest elevation. And finally, it's okay, just add it into the result. And we'll save our model. And now we need to add it inside of our interface. So we go ahead, we'll just load the previous one that we had, and just need to add it here. So we'll just add it, and it will be the crest elevation. Okay. Now we just need to regenerate our DLL. So go ahead, simulation, regenerate GoldSim configuration, and that's it. We should be able to run it. So now not only does the deposition, but if there's not sufficient freeboard, it will also raise the dam. So I'll just like fast forward it. And we can just check the results, make sure that the dam is actually the crest level is being plotted, and you can actually raise the dam. So as you can see now, we are raising the dam. For now, we only have done one realization, so it's not actually a Monte Carlo simulation. I'll just quickly just show you once we'll just add a second one for now. And I'll show you after a model that can completely run. It's just to show that actually is it working or not. So same thing, I'll just fast forward it rapidly. And now we've run a year of simulation every single month, and we have the dam that's raised, and we've got different realization of the future. All right, so now I just want to show you the model itself. I'm just gonna. So that's the. So we've got our throughput volume. As you can see, we've simulated multiple times. We've got different results every single time. And then what we after is actually what's our elevation. So we run it multiple times, and every time it gives us different results. But ultimately, we want to look at the probabilities so that we can see, well, when do you actually need to raise your dam? So for example, in that example, we're raising the dam from the dam can be raised from as early as the third quarter of 2027, or it can be as late as mid-2029, for example. But most likely, it's likely to happen within this band, so like towards the middle of 2028. All right, so now we have a model that is able to run some deposition and run fairly complex dynamics that are happening within your tailings storage facility. So now we get into the part of like, well, why would you want to use like such application? I'm just gonna kind of like present it from the perspective of my journey into GoldSim modeling. And I come from a background in like site-wide in water management in general, but I specialize rapidly into like mine water management. And when we look at systems like a mine systems, they are highly dynamic and very difficult to predict. And the model that we use in water, which are hydraulics and hydrology model, which are very accurate and contain a great level of details, but they're limited in terms of addressing the interconnected nature of a mine water system. So to some extent, you need to lose some of the granularity so that you can actually gain some perspective about how your systems behave. And so at the very beginning, when I started using GoldSim models, it was really to try to get like those water balance, which was at the time in South Africa required for compliance perspective. And it was really trying to like put the various parts together, because you've got some lines that are being you've got different parts that are being monitored, but not everything is being monitored. So the idea was to kind of like, what can we have a full picture of what happened in the past? So it really allows us to reconnect the various parts and see, well, also how does the monitoring components are working with each other, and sort of like target improvements going into the future. But it's essentially reconstructive. And limited to like looking at simulations in the past. Then I got into like more developing predictive models. And once we get into like predictive models, it might be for the sizing of specific structures, like a water treatment plant or ponds or storage dams. But essentially, it's still limited in nature in the sense that you have a specific, it's gonna be limited in time, this interaction. And you're looking at a specific life of the mine plan. You're not looking at the entire envelope of the various possibles, but now it allows you to evaluate a range of scenarios and have some kind of like a proactive management and informed decision making. And then finally, it's more like now looking at it from like a systemic level, where the model is part of an overall governance of the system, and it's regularly updated. It allows us to basically track how the system is, and you've got various like early warning system to see, well, how much does it change, and you plan for the various contingencies that could happen as well. So it's a lot more in terms of anticipation of the risk and mitigation of those risks. So I like to use the analogy of like steering of a ship and the fact that those systems are highly dynamic, and it's a bit like actually a river, because we here, like in a very schematic way, looking at just like the future of one potential variables, but in reality, you've got multiple variables, you've got multiple objectives, and those might be conflicting as well. So ultimately, you've got complex systems that are entangled with each other, and so web of issues and solutions. So it's not just to one problem you have a solution. And one needs to realize that if we want like a specific future, it will be not just a model outcome that will lead to that specific future, but it will be a whole bunch of decisions made all along the way. So it's a highly interconnected system, and yet because of our backgrounds, we tend to isolate and then concentrate on the elements at kind of like the disciplinary level. So we possess a knowledge of the details, but yet often we've got like poorly defined goal. So a tool like GoldSim really allows us to kind of like step out, and it brings sort of like a point of encounter to see actually how does the whole system work with each other. So it's an opportunity to bring together the various assumptions by various actors and different disciplines, the data, the models, the people, and do rounds of actually confronting those to see, well, how does that vary? And ultimately what comes out of it is we've got a different understanding of the system, but also we understand that this system is varying, and we need to keep track of how much is varying so that we can constantly learn about it. We can reduce the potential possibles by improving our knowledge of the system, but also knowing that some of those will vary because of external limits as well. And so out of each of those encounters, we have reframe questions, better coordination in terms of our efforts, informed decisions, and plans that can be adaptive. And this type of approach, it's about like keep on learning, and the GoldSim model is really about learning, the journey of learning. So it brings us a holistic understanding that is really important for proactive risk management and improving the collaboration. So it leads really to actions through objectives rather than detail. So how does that apply to TSF? Well, TSF it's both adapted and it's both adapting to the TSF complexity. It's a system that we need to look at from a very long lifetime, like beyond just the closure of the mine, because they will stay there. They're complex, evolving systems. They're likely to be impacted by climate change, and there's a number of global standards that keep on changing. And also we're dealing with like rapid development of new technology. So GoldSim is really a great tool to actually deal with such systems. There's many ways that such things could be applied. I've put like different user case stories. I just want to show you a couple of examples of them. So this one is just like the estimating the cost of the operations, and it's really, well, as a TSF manager, I want to estimate the operational cost and the different scenarios, including the variations in your material handling and the weather conditions to ensure budget allocations are adequate. So I've just taken the model that we ran earlier on, I just complexified it a little bit. So where earlier on we just had a pond volume and a throughput, actually used the throughput volume. Now actually I replaced it with a throughput tonnage. I added some uncertainty around the density, but what I want to show you is that we actually started working at, well, what is the cost of both the deposition of the tailings and the cost of the raising of the dam. So we've set up some cost for it. So for raising the dam was the cost for both the permit, the engineering, the moving of the infrastructure. So we've got a cost per cubic meters, and we've put it as like kind of like an estimate of it. We've done similarly for the deposition rate. So we've got a cost of, in terms of dollar per ton. And based on that, what we had earlier on, where we look at, well, how is your structure raised? Now we can actually work out what is the cost, and that's the operating cost associated with that. So a very simple model, but the idea is, well, to look at, well, ultimately what sort of, over the life of your facility, how does that cost vary? And so in here, we can have a look at it, and we see that ultimately, over the entire simulation, it gives us a cost where it's between 5 and 5 to 6 cubic dollars per ton for the most likely, but it could go as low as 4.5 or as high as 7.5 in this specific example. Another one could be, well, looking and evaluating various scenarios. So it could be like a change in technology. It might be like a new tailings dewatering technology, for example. And same thing, I just reused the same model. The only change that I did in this case is, well, I looked at in between keeping the spawn of the volume. So in this example, actually, I've got monthly average. So actually, we've got a pond volume that sort of like goes up and down according to some kind of seasonality. But we've got a second option where we look at, well, if we implement like a different dewatering technology or impact inside of the mine mode system, ultimately we can get to like a lower level inside of our pond. How does that affect actually the cost, for example, of our OPEX cost? So in this case, we dropped the volume from 1.7, 1.6, 1.7 million cubic meters of water to dropping down to like 1 million. So like around 60% of its operating capacity. And ultimately we get distribution. So you can see that actually the cost that we had that would go up to 7 now goes up to like 6.5. And then you can see, well, how does that dropping the water operating level change the actual storage capacity and ultimately change the cost of the operations. All right, and I'll show you a final example. And this one is about analyzing tipping points. It's about seeing, well, is there specific design criteria that when you actually reach those design criteria, maybe your system fails? And there's various things that can be assessed. But in this specific example, I'm actually running a deposition on a ring dike. So we're doing every month the deposition along that ring dike. So it keeps on like actually doing the deposition all around. It's actually a multi-stream deposition because we keep depositing all around. And we've got various distribution all across the system, but what's important in this case, it's about assessing specific design criteria. So we use Muk3D to actually, because it's got lots of tools for geometric analysis, we actually use it to calculate specific things. So it might be the thickness of the tailings that's being deposited on a monthly basis so that you can better estimate the desiccation rates. It might be the flooding capacity that you have within your system as the upstream construction dimension raised. It might be your rate of rise or the height of the total height of the facility that might be important for the hydrogeologist or the geochemist for closure, for example. Or it can be the minimum distance from the pond to the crest. So not only we'll do the deposition run, but we'll do the design criteria calculation. So I'll just show you how the model is being run, and you'll see that it does all the various runs. And ultimately, I just want to show you the actual model. And now you can see we've done the deposition. Actually, towards the end, actually raised the deposition as well. But what we want to see is some of those design criteria. So, for example, we've got what is the distance from the pond to the crest. And maybe you've got a new design criteria that it should never reach, for example, 400 meters. And as your footprint is decreasing, as the dam is raising, now you actually have less. You might find, well, when do you have actually serious risk on your facility? But earlier on, I mentioned as well the deposition thickness. So in this case, you see that 95% of your tailings on a monthly basis, you get 40 centimeters of tailings that are being deposited in your tailings facility. But really, that tool is now is used to analyze like further some design criteria. Okay, so oops, I'll just go back there. What's the current state? At this stage, you have a tool that allows us to run Monte Carlo simulation of TSF geometries. It does have some limitations. I would recommend it to use it for like fairly long term, where you don't have as much detail in terms of the deposition and you don't need as finer grains and fairly simple designs. I would not advise it to use it for short term and operational use. And the reason for that is mainly from a computational requirement. not on it, and it's something that's quite recurring with Monte Carlo simulation, but of course it does take some time. So better start with like grids that are fairly not detailed too much, and time steps that are fairly big. There will be major upgrade in the next Muk3D release, where it will use the graphic cards, and it's serious, like it will really reduce a lot the time to actually run those models. The other limitation is from a pedagogical perspective, is people are not necessarily used in the TSF industry to deal, well in many industries, but and this one as well, in terms of using probabilities and assessing risk as like something that varies. And then the other one is ontological. Is the scale of the project might not be adapted necessarily to the scale of like a systemic model. So this is it for this presentation, and thank you very much all, and I'm looking forward to your questions.
Thanks a lot, Simon. We'll take any questions that anybody has at this time. You can go ahead and type it in the chat inbox there. And also, if you have any follow-up questions afterwards, you can feel free to reach out to us and we can forward them over to Simon.
Running a deposition, so we're not actually running any sort of like consolidation on the grid. There are some very basic tools to do that within Muk3D, but in none of the examples did I use that in this presentation.
Okay, yeah, and another question is, this is, I guess, to me, will this be available online to watch again? The answer is yes. We are recording the presentation, and it will be in our webinar archive location in our library. Somebody else asked, how difficult is it to incorporate a Muk3D simulation model into a fully fledged water balance model that can, for instance, have 3 TSFs?
So I wouldn't recommend to have, I mean, it's something that is possible. I think what I mentioned like towards the end of the presentation is, I think the big one is the cost in terms of time of computation. So yes, it is feasible, and it's not too difficult to do. I think the big issue is how long it takes to actually run your model. So I would suggest you start with fairly basic models, and you keep kind of like increasing the complexity to see what you can do with it. As I mentioned, I would try to avoid the operating model, and it's for 2 main reasons. One, your grids tend to be a lot more complex, a lot more finer. And all the deposition runs, you might have like multiple deposition lines and operations. So the model itself is a lot more complex, and as well from the GoldSim side, you will tend to have, if you use like actual history, you tend to have distributions that are more complex, and therefore you need to actually have more realization of the future to have something that that is meaningful. So the limiting factor is not the development of the model, it's the actual time of computation at this stage.
Sorry about that. The next question is it possible to change the beach tailing slope as a variable?
Yeah, so in one of the examples that I showed, I think it might be this one actually. Yeah, you can change whether you use a linear distribution or use like a compound slope. You can change those, and it's part of the Muk3D API, where actually within the code you can you can change both the slope and the distance if you've got compound slopes, like the distance where you have those ones. But yeah, I think it's in this model actually that that I showed towards the end that was included.
Okay, great. And I actually don't remember seeing this either, so I'm going to ask the same thing that someone asked. How can you remind us again how you're dealing with stochastic rainfall in this model?
In this model, it's just like I use the model from e-water to actually fit like I don't know, the Australian e-water to fit a distribution, and ultimately I've got a time series which has got 2,000 years of rainfall, and I just changed the what is it called again in GoldSim? Time series. What is it called? Time series shift to actually shift annually in between each of those years that have been simulated outside of GoldSim. So it's not actually a stochastic model within GoldSim, it's external.
Oh, okay.
Yeah.
I'll have to check that out. I've never looked at how the e-water tool does that.
Yeah. It's the Boughton simulation is a good paper on that.
Oh, of the Australian water balance model.
Yeah.
Yeah. So you're just taking it.
No, not that. It's another. Is it Boughton? Maybe. Okay, I'll have to quote. No, I don't. It's a different one. It's not the AW. No, it's something else.
Yeah. Okay. Okay. And let's see. Another question it looks like for me is, are there upcoming webinars? So yeah, you can just go to our website at goldsim.com and then go to customer care, and you'll see in their learning resources, just click on that and you'll see there a whole section on all of our upcoming webinars. So other than that, are there any other questions before we end the webinar?
I'm just going to share in the comments for that paper on the daily rainfall.
Okay, great.
If I can.
Somebody made another comment saying the software has some hints or tables or some typical values for different variables for different minerals, such as, and I apologize, I don't know mineral names very well. AU and CU.
No, it doesn't have. It doesn't have any of the. It's a generic model, so it's up to you to actually enter those values.
Okay, great. And those of you that are still on, note in the chat to everybody, Simon posted the reference for the name of the rainfall generator. I'll have to take a look at that. I wonder if it's based on the WGen model that we have in our library.
I don't think so. No.
Okay.
It's a different one. Yeah.
Okay. All right. Interesting. Thanks a lot, Simon, for your time. It looks like our questions are wrapping up here. So those of you that still have more questions, please reach out to us and we can help you out with that. And also have a look at our archive once that gets posted, probably tomorrow or early next week. So Simon, did you have anything else to add?
No, that's it. Thank you very much for attending it.
Okay. Yeah, thanks again, Simon, and we'll see you all next month.
Okay, cheers.